recurrence is a very common and useful idea when it comes to modeling the development of mathematical systems. It is widely applied in many areas of pure and applied mathematics, such as recursion in computational methods and integer sequences in number theory. And, as you might expect, it also plays an important role in combinatorics. Let's begin with some definitions. A recurrence is the relation we establish between the elements of an ordered set when each element is defined in terms of previous ones. For example, consider the set of all natural numbers, denoted by capital N. Each element can be given an index, an, indicating its position in the sequence. In this case, we choose to start our sequence from A0, but that is just an arbitrary choice. If convenient, one may instead start indexing from A1, for instance. The recurrence appears when we express our general term an as a function of its preceding terms. Here, we can define a recurrence relation as follows: an equals an minus 1 plus 1. This simply means that each element in the set is just the previous element plus 1. Therefore, the whole set can be described as the sequence of all an, such that a0 equals 1 and an equals an minus 1 plus 1. From the perspective of combinatorial analysis, recurrence is extremely powerful. It allows us to tackle complex, large-scale problems by breaking them down into smaller cases, solving those, and then building them back up to fit a more general case. In practice, there are many different approaches to doing this, ranging from very intricate and specialized methods to much simpler ones. Here, we will only cover the main ideas for solving a recurrence without going too deep into technical details. If you want to explore further, there are plenty of excellent examples in the references. Before going on how to solve them, let's first see how one can deduce a recurrence relation from a problem. Take this question in hand. A certain species of tree was noticed to be such that each of its branches, after 2 months, would raise a new one, which from then on would go to produce another branch every month. The tree, as a sapling, contains only a single branch, which must wait 2 months before producing its first offspring. How many branches will this tree have after n months? Well, from the problem statement, we already have that our a0 should be 1, since at t equals 0, i.e., at the initial time, we only have one branch. From this, we can define a sequence fitting our conditions. Since the sapling must wait 2 months before producing another branch, we have that our a1 should also be 1. That is, at month 1 we still only have one branch. From month 2 and on, we can draw a diagram to visualize our growth. Here, we are representing each branch as a stick, with its color indexing the month in which it was generated. It may not seem so from the initial cases, but this sequence is actually growing very fast. To better show this, let's look at a simulation of our tree. In this case, we only care whether a branch is older or younger than 2 months, as the behavior doesn't change for branches any older than that. So, we are only going to index up to that age, coloring newborn branches light green, 1-month-old branches green, and all older branches brown. Opening an addendum. Here we are using branch as a very general term. Technically, the first instance wouldn't be considered a branch, but we are saying so for the sake of simplicity. Going back to the simulation, like in our sequence, at month 0 we only have one branch, which will only grow after 2 months. Let's fast forward to month 5. As predicted, we have 8 branches, but let's look in on how the sequence grows past this. Here, we are at month 8. At this point, it's already quite difficult to count all the branches. After just 3 months, we have more than tripled our previous count. Comparing the numbers more closely, from month 6 to month 9 alone, the tree gained 26 new branches, and this rapid growth only accelerates. Looking in hindsight, by month 10, we would actually be looking at an astonishing 144 branches. Here's when recurrence would come in handy. Let's try to establish one by looking at our first sample cases. Clearly, we can state that the branches at a future time do not disappear, or in more mathematical terms, the branches at time t equals n minus 1 still exist at time t equals n. From this, we can say that our recurrence should be of this form, where the term an minus 1 represent all the branches at least 1 month older. Based on another statement from our question, we can also say that only branches at least 2 months old produce new branches. That is, only branches at time t equals n minus 2 can produce new branches. So we can say that our n from the first equation should simply be the branches at a time 2 months before, or, in terms of our sequence, an minus 2. Gathering these two results, we can create our recurrence relation by the system, an equals an minus 1 plus an minus 2, where a0 equals 1 and a1 equals 1. This is the recurrence we were looking for. As some of you may have noticed, this result is quite a well-known mathematical object. The growth pattern we observed is actually following the Fibonacci sequence, also known as the golden numbers, often seen when modeling behaviors in nature. Namely, as previously said, many famous integer sequences originate from a recurrence model, so seeing an appearance of the golden numbers here shouldn't really come as a surprise. Taking that into account, let's now take a look at another problem that leads to a famous sequence. Let an be the number of sequences with n pairs of open and closed parentheses. For a given n, how many valid sequences of parentheses are there? Logically, a valid sequence here would mean one that actually has proper meaning in the context of placing parentheses, one you could actually use, like a sequence a computer would understand. More formally, a valid sequence is one where we never close a parenthesis before opening one. As an example, take n equal to 3. Here we would see that the first two cases are valid, but the latter two are not, because a closing parenthesis appears before its matching opening parenthesis. With that in mind, let's go back to our question and try to get a feeling for our recurrence by looking at some sample cases. As usual, the initial terms are quite small, so let's increase n a bit. Let's try n equals 5 for good measure. This one grows even faster than the Fibonacci sequence. At just n equals 5, we already have 42 valid cases. Since we didn't see a big increase at the start, this must mean we are looking at a really high-order recurrence. Going back to our initial cases, we can obtain a recurrence relation for an by focusing on the first opening parenthesis, i.e. the leftmost one, and the closing parenthesis that matches it. For any valid sequence of n pairs of parentheses, we can say that inside the first pair there may be at most another k pairs, and, by consequence, outside of it to the right, n minus 1 minus k pairs. If we denote the number of possibilities for n pairs by an, then, if there is nothing inside, that is, k equals 0, the outside has n minus 1 pairs, giving a0 times an minus 1 possibilities. Or, if there is one pair inside, that is k equals 1, then necessarily there are n minus 2 pairs outside, making for a1 times an minus 2 possibilities. Take our one pair, or n equals 1 case for instance. Denoting the lack of pairs inside by the empty set, see our total possibilities for it would be a0 times an minus 1, or better, a0 times a 0, implying a 0 equals 1. Looking at a broader case, for n equals 3, we could either have 0, 1, or 2 pairs inside, varying our k from 0 to 2. Making these calculations, we have that. At k equals 0, there are a0 times a2 possibilities, which equals 2. At k equals 1, there are a1 times a1, which equals 1. At k equals 2, there are a2 times a0, which equals 2. Summing that up, we conclude that a3 equals 5. Generalizing for an n-pair sequence, we can induce a formula for our an. Pairing now with our initial conditions, we can get the final system of recurrence. This system generates what's known as the Catalan sequence, named in honor of the French mathematician Eugène Catalan, and, pun intended, is quite recurrent inside combinatorics, being hidden in all sorts of seemingly unrelated problems. Now, actually starting into how to solve these equations, we're going to be using three methods: the backward substitution, the characteristic equation, and the generating function. Starting with backward substitution, this is the simplest method for solving these types of equations. It relies on the repeated application of the recurrence relation, beginning at an arbitrary element of the set. Take this recurrence as a reference. By repeatedly substituting an minus 1 for its recursive definition, we can expand our equation like this. This develops our equation into the sum of a geometric progression with ratio equal to 2, which would equal 2 to the power of n minus 1. Now, it's important to take note that, albeit easy, this method has a bit of a caveat to it. The result you get for the recursion is not necessarily valid, but that's an easy fix. You just need to check whether or not it fits the recurrence. Let's check whether 2 to the n minus 1 fits our criteria or not. It does, so now we know our result is valid. Now, before introducing our second method, I need to state a few definitions. Our characteristic equation theory is being only applied to homogeneous linear recurrences. That is, recurrent systems of this form, where we define the general term solely as a linear combination of the k preceding terms, with no additional terms inside the function. In more certain words, a recurrence relation of order k is called a linear homogeneous recurrence if, and only if, each term, an, is expressed as a combination involving only addition and scaling of the k preceding terms, where all the scaling coefficients are constant. Also, take note, since each term an depends on the k previous terms, we must specify exactly k initial conditions in our system, here represented by the capitalized constants ak. Moving on to what the characteristic equation actually is, given any homogeneous linear recurrence, we can substitute an with x to the n to define its characteristic polynomial equation, which takes this form. By simplifying a little and dividing by x to n minus k, we get the final form of our polynomial. This is our recurrences characteristic equation. It turns out that by analyzing the behavior of this polynomial's roots and using a few arguments from functional analysis, one can express the solutions of this characteristic equation in a useful manner. Call lambda 1 up to lambda L the distinct, non-zero, possibly complex roots of our characteristic equation, with respective multiplicities m1 up to ml. There exists a set of polynomials, p1 up to pl, of bounded degrees such that the general solution of the recurrence relation can be expressed as this combination. The full proof of this result is not particularly convoluted, but it does require a considerable familiarity with concepts from linear algebra that we haven't covered in this video, so instead, we're only going to focus on its overall applications. Looking at the simplest case, where the characteristic equation has k distinct roots, lambda 1 to lambda k, each with multiplicity 1. Since each root is linearly independent from the others, meaning you can't write any one of them as a scaled or added combination of the others, our solution is the sum of exponential terms. Each sequence, lambda to the n, is itself a solution to the recurrence, and because of linearity, we can combine them. Now suppose some root is repeated. For example, a root lambda appears with multiplicity m greater than 1. A single term, lambda to the power of n, is not enough to produce m-independent solutions. They would be linearly dependent. So we need a workaround. Here's the trick. For a repeated root, multiplying by powers of n makes them linearly independent, while still satisfying the recurrence. You can't write n times lambda to the power of n as a constant multiple of lambda to the n, as that would imply n is constant. By scaling with n, we create new independent solutions without breaking the recurrence condition. Actually applying this, our general term should look something like this. Take note that here, only the first root, lambda 1, has a multiplicity greater than 1. For the case of complex roots, they always appear in conjugate pairs. Rewriting lambda and lambda bar using Euler's formula, we get this for each instance. This produces a real-valued combination with sine and cosine. From these real combinations, we can then apply the previous results without any restrictions. Emphasizing what I said previously, the full justification of these results relies on theory that we have not covered here. So, I'll just ask you to trust me when I say that these are the correct results. Let's revisit the Fibonacci sequence we previously deduced, and now try to solve it using this new method. Tidying up the general term and denoting it in terms of x to the n, we have that the Fibonacci sequence's characteristic equation is the following. Now, using the quadratic formula, we can find the roots of this polynomial to plug into our formula. For clarity, we will name our roots phi1 and phi2. Take note that here we have two distinct roots, each with multiplicity 1, so our solution falls within the first category discussed. Substituting into our general solution, we get this equation, which we can solve using the initial conditions. The solution consists only of solving this system of equations, so I'm just going to play a few animations going through the process. You can pause if you want to take a closer look. From the system, we find that our coefficients, delta 1 and delta 2, are 1 over square root 5 and minus 1 over square root 5. Substituting now into the equation above, we finally get the closed form solution of our recurrence, in this specific case known as the Binet formula for the golden numbers. It may seem strange at first that a formula meant to output only integers involves irrational numbers such as square root 5. However, if you plug it into a calculator, you'll see that for any integer n, the square roots cancel out, leaving an integer result. An even more interesting observation, though, is that due to the second term being negative, this function is actually complex valued for any n outside of the integer domain. This isn't really a problem for us because we define the function based on a sequence, so we only input natural numbers. Nevertheless, let's take a look at the expanded version of this function over the real domain. Due to the complex output, we will graph the real and imaginary parts of this function as separate entities, with the red graph representing the real part and the blue graph representing the imaginary part. The imaginary part here is very small, so I'll scale it up a bit. Let's look at the points where x is an integer. Label them Fn. Here, as expected, the imaginary part zeroes out at all our domain's original points. I know there's no real way to verify this just by looking at the graph, but notice that all of our points map to integers too. Let's skip to F10. Looking back at the full view of the graph, we can see that our function perfectly matches the sequence. I think it's worth mentioning that here we only showed the positive x inside our amplified function, but the behavior for the negatives is almost identical. Plugging our function into Wolfram alpha, we see that it produces an almost matching shape for negative integers. The only difference is that all the even n terms are negative instead of positive. For the last method of computing recurrences, the generating function, we will need to lightly draw on some tools from differential calculus, but nothing too outrageous. A classic topic in the study of calculus is the representation of a function as a power series, an infinite sequence of this form. Power series are very useful analytical tools. They have very few algebraic restrictions and can be manipulated like any other usual function. They can be added, subtracted, and multiplied without problem. So, perhaps unsurprisingly, much like the characteristic equation, power series can be extremely helpful in analyzing a system of recurrence, encoding the scaling behavior of the sequence. Before actually starting, it is important to note that, in our analysis, the convergence of the series is not really a topic of interest. We are only considering it as a kind of blueprint for our system, a formal series. However, in cases where it does converge, we can, if convenient, use techniques from calculus to express the series in more concise forms. Starting from any recurrent sequence, we can associate a power series, f of x, to our system by mapping the coefficients kn to our general term, resulting in this formal series. This polynomial f of x is the sequence's generating function. An incredibly clever idea for finding the general term from these functions originated in the early work of the French mathematician Abraham de Moivre in probability theory. He devised that one could always establish a functional equation in terms of f of x for any arbitrary sequence, and from this, algebraically derive an explicit formula for the coefficients, that is, a formula for the general term, an. Take this recurrent system as an example. Adding in our generating function and substituting for an, we have this as our formal series. Developing now in the same manner as a backward substitution, we can establish our functional equation as follows. Here, we are recursively applying the definition until we can match our summation function with our function's definition. The relation we found implies the functional equation f of x equals 1 plus 2x f of x, or more simply, f of x equals 1 over 1 minus 2x. The idea for solving the general term from here is based on comparing the coefficients of the powers of x between our two equations for f of x. However, notice that our second definition of f of x is not actually in polynomial form, which means we cannot directly compare the coefficients as of now. This is where we need to apply some results from calculus. Disregarding justifications, we know from the study of Taylor series that any analytic function, which includes all of our usual functions and their combinations, can be expressed as a full-fledged polynomial in terms of its derivatives. This result gives us what is called a Taylor polynomial, and it is what will allow us to establish a comparison between our equations for f of x. To express our function in terms of its Taylor polynomial, we first need to look at its derivatives. Writing a few of them out, we can observe a constant pattern emerging from the subsequent differentiation, inducing the form for each derivative to be this. Take note that the x in this equation is arbitrary. In our case, we will always be substituting for x equals 0. Returning to Taylor's formula, the polynomial transforms to this. Simplifying now, we finally arrive in a form that can be directly compared. Let's place both instances of the formal series together. Since they are equivalent polynomials, as previously said, to find our general term, we can simply pair each of the coefficients at each degree. Without any major analysis, just from the last term we can already conclude that our an is equal to 2 to the n. This is the final solution to our recurrence. In this particular case, some of you may have noticed that using Taylor polynomials is not strictly necessary. There is a parallel solution by observing that our second formal series is actually in the form of an infinite geometric progression sum of ratio 2x. So, by default, we could already express it in the final form we got from our Taylor series, cutting out all the work we had to compute it. I'm pointing this out to emphasize that sometimes there are shortcuts to solving a recurrence. The Taylor method is a general and reliable way to solve it, but it is by no means the only one. So, if you feel confident in your understanding of sequences, take a moment to analyze your function first. You might save yourself a lot of time. Looking again at a previous example, let's try to find the general term of the Fibonacci sequence, making use of generating functions. As we have already seen a couple times, the Fibonacci sequence is defined by the recurrence an equals an minus 1 plus an minus 2. So, defining the generating function and substituting for an, we have this. Following the same steps, we can develop this formal series into a functional equation, leading to this alternative form for our f of x. From here, we could already apply the Taylor series and call it a day. However, there are a few things we can do to make our lives easier. Turns out this case is a perfect application of the technique of partial fractions, which consists in breaking down a rational function into simpler parts. First, let's express the denominator in a more convenient form. Matching our polynomial's coefficients, we can rewrite our quadratic in function of the roots we calculated previously, now phi and psi. From this, we can rewrite our rational function as a combination of this sort. Solving now for the constants a and b, we can form a system of equations arising from the equivalence condition. Here we have found a equal to 1 over square root 5 and b equal to minus 1 over square root 5. Substituting back into the generating function, we obtain this equivalent form. From this point on, you can apply Taylor's formula without any hardship. In fact, this simplified form is analogous to what we did before, the only difference being you need to expand each smaller rational term and then add them up together. To save time, we'll skip the intermediate algebra and go straight to the result. Once again, we have arrived at the Binet formula for the Fibonacci sequence. Going now for our last method of counting. The reflection principle is an interesting geometric idea used to solve counting problems with bound-type constraints. Something of the sort of an amplitude in quotes, in which the results can vary between. To show this, let's take a look at a graph. The graph you are seeing here is what's called a polygonal path, a graph drawn using only lines and integer lattice points as vertices. In the case of the principle of reflection, and as a matter of fact any area inside combinatorics, these graphs denote what's called a stochastic process, which is just a nice way to say you are showing how a random process went over time. You can also probably notice this from the graph, but if you were to imagine the vertices at each lattice point, you can see that our lines are only either going up or down at each instance. So by nature, we're describing binary random processes, either ups or downs. Outside of this introduction, let's break down what's left here. This polygonal path in specific is going from 0, 0 to an arbitrary point, AB, and in our use case for this principle, they all necessarily have to. The C line here is the bounding restriction we talked about earlier. The problems we will be solving with this are all about the polygonal paths that go to AB without ever touching it, and is what we will be discussing from now on. Let's take a look at a few possible polygonal paths. How could we count the total amount of paths from the origin to AB here? Well, turns out the idea is really simple. Remember, we are dealing with a binary process, so we can just denote each graph as an ordered sequence of ups and downs and run some permutations. For the sake of organization, we will be indexing ups as x and downs as y now. For a path to end at a height b, the number of steps up and down must satisfy the equation x minus y equals b. In addition, we also know that the total number of steps, x plus y, is equal to a. Solving this system, we can get an equation for our possible paths in function of a and b, denoted here by the t function. Now that we know how many paths we have for an unrestricted setting, let's introduce our C-line back. The trick here, which is what names this whole principle, is that we can reflect our function by the line's axis to count the paths which cross the line. See, the last point in the reflection is invariant in all possible polygonal paths, always ending up at 2c minus b. Take our previous purple path as an example. See, it also ends up in the same point as our first reflected function. The reflection here is actually a bijective function. So by counting all the cases that end up in the reflection, we also indirectly count all the cases that end up crossing the line at some point. This makes our valid cases to be the total number of paths minus the reflected ones. Plugging the reflected point into our previous formula, we have, which together with our previous result makes for this final formula for the valid paths. With this now in hand, for example, we can solve the parentheses problem we had earlier without even using recurrences. Let's first revisit the question though. Let an be the number of sequences with n pairs of open and closed parentheses. For a given n, how many valid sequences of parentheses are there? Note that this problem is a perfect example of a binary sequence, modeling the opening and closing of the parentheses. Graphing a random sequence, we can follow the same steps we did before, just substituting our a for 2n, as in the total number of parentheses in n pairs, and b for 0, since in the end we need to have as many closed parentheses as open. For a more concrete example, assume n equals 7. Here, our condition of not closing a parenthesis before opening one directly translates to never crossing the line at c equals minus 1. Applying the reflection principle, we now get our final result as this.